We are starting on page 6, which is example 1. It says that the amount of wheat in storage after t weeks is given by the function w of t equals negative 1.04t plus 15.6. W of t stands for the amount of wheat in thousands of pounds, and they already told us that t is the number of weeks that it's been in storage. So it asks us first, is the function increasing or decreasing, and how can we tell? Well, first just observe that this is a linear function. It has the form y equals mx plus b. M is negative 1.04, b is 15. Remember that m stands for the slope of the function. So this is slope negative 1.04. Since the slope is negative, we know that this function w of t is decreasing. Next, it asks us to interpret the real-world contextual meaning of that increasing, decreasing behavior. So I want to be as specific as I can. I actually want to get down into the nitty-gritty of the meaning of that number negative 1.04. When you're interpreting a slope, I always recommend that you write that slope as a fraction, because we know the slope is always change in y over change in x. Change in output divided by change in input. Now in this case we don't have y's and x's, we have change in w of t, that's the numerator, divided by change in t, that's the denominator. So I've written it as a fraction. I've kind of noted next to it what each value means. The negative 1.04 is the change in w of t. The 1 is the change in t. I might also add units to the top and units to the bottom. So the w of t stands for thousands of pounds of wheat. So the change in the thousands of pounds of wheat is negative 1.04. And the denominator, the t's, stand for weeks. So the change in the time is weeks. They're saying on this graph, if you increase 1 week, you would decrease by 1.04 thousand pounds of wheat. A better way to say that would just be 1,040 pounds of wheat. Now this is consistent and constant. It's a linear function. It does this every single week. It's saying every week that passes, the amount of wheat in storage decreases by 1,040 pounds. It asks us to identify the y-intercept. Again, this is the form y equals mx plus b, and b represents the y-intercept. So our y-intercept here is 0, 15.6. Points on this graph have input value t, output w of t. T represents the number of weeks that have passed. W of t is the thousands of pounds of wheat in storage. So it's saying at 0 weeks, meaning to start, there is 15,600 pounds of wheat in storage. Part C asks us to identify the x-intercept. Remember, an x-intercept, the y value is 0. So the output is 0. So for our function, I'm going to go to my equation. I'm going to let the output equal 0. And I'm going to solve for the input t value. So we can go ahead and add 1.04t on both sides. We have 1.04t equals 15.6. We divide both sides by 1.04. Pop that in my calculator and I get 15. So when output w of t is 0, the input is 15. Again, interpreting what that means, the input t is 15, the output w of t is 0. They're saying after 15 weeks, there's 0 pounds of wheat remaining in storage. Part D asks us to find w of t equals 4. So they're saying the w of t is 4, the wheat is 4. So we let the output equal 4 and we solve again for the value of t. So here we can go ahead and subtract 15.6 on both sides, and then we'll divide by negative 1.4. I get about 11.15 for t. So the input is 11.15, the output is 4. So at 11.15 weeks, there is 4,000 pounds of wheat left in storage. And lastly, we want to find W of 4. So instead of W of t, it's W of 4. So we're replacing the t with 4. We're evaluating the function at an input of 4. So I'll just pop that expression into my calculator. I'm getting 11.44. So W of 4 is 11.44. And that's saying after 4 weeks, there's 11,440 pounds of wheat remaining in storage. On page 7, example 2, this time we see that the amount of solar power installed in the U.S. has grown since 2000. The amount of solar power installed can be modeled by this function m of x, and that means it's outputting the amount of solar power installed in megawatts, and it's saying that the input is the number of years since 2000. So first it asks, is the function increasing or decreasing? I notice that this has the form y equals a times b to the x power. It is an exponential function. Since the factor b, the base of that exponential, is greater than 1, we know that this is an increasing exponential function. Now we can get more specific about exactly how it's increasing. The factor is 1.46. Remember that factor is equal to 1 plus the decimal rate. So we have 1.46 equals 1 plus the decimal rate. If we subtract 1 on both sides, we see that the decimal rate is 0.46. So the way we say that rate is as a percent, 46%. So every time x increases 1 unit, the y value increases 46%. In contextual terms, they're saying every year after 2000, the amount of solar power installed in the U.S. increases 46%. Next, we're asked to identify the y-intercept. Again, this is an exponential formula, a times b to the x. The a represents the y-intercept. So 15.45 is the y-intercept. If we were to write it as a point, it's 0, 15.45. In this function, x represents the number of years since 2000. So 0 years after 2000, that's the year 2000. And m of x represents the amount of solar power installed in megawatts. So they're saying in the year 2000, at that time, there is 15.45 megawatts of solar power installed. Part C asks if the function's concave up or concave down. I would expect you to understand the shapes of these exponential functions. This is an increasing exponential function, so it looks like this. It is increasing concave up, and as the x diverges down towards negative infinity, the y values get closer and closer to the x-axis down here. So it's definitely concave up. It asks us to interpret the real-world meaning of the fact that it's increasing concave up. So the fact that it's increasing is meaning as the years go by, there's more and more solar panels installed. But the concave up is telling us that as the years go by, it's increasing at a faster and faster rate each year. Part D asks to identify the right tail end behavior. So on this graph that is increasing concave up, over here on the right tail, in limit notation, we'd say the limit as x diverges to infinity of our m of x function is infinity. It is diverging upward, it has no bound. We're saying as you walk to the right, if you imagine walking to the right on this function, walking to the right, your height would go up, 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 up without any bound whatsoever. Now, if you think about that in real world terms, you're saying as the years go by, as you go further and further to the right, your years go by, the amount of solar panels installed increases without bound. Lastly, it asks us to solve m of x equals 20. So we're saying the y value is 20. For this problem, you could use logarithms to solve the equation, Or you could use Solver on Excel to solve the equation. So in Excel, I have put in column A X values. I just picked X values spanning from 0 up to 20, so the year 2000 up to the year 2020, and then I plugged in the function m of x, 15.45 times 1.46 raised to the x. And again, this is asking us to solve when the m of x value equals 20. So I'm going to go through here and I see it must occur somewhere between year 0 and year 2. You see that the y value is 15.45, and then it goes up to about 33. So somewhere in between, it reaches a y value of 20. So I'm going to put my cursor here in cell B3. It's going to be close to 20. I'm going to force Excel to change this cell to y equals 20 by finding the x here in cell A3 that produces a y value of 20. All right, so put your cursor in cell B3. You go to Solver. In Solver, I set the objective cell to the cell B3, where my formula is. I'm going to change it to a value of 20 by changing the X value cell. I hit Solve, and there it goes. It says it's about 19.99999 when the X value is 0.68. So midway through the year 2000, the U.S. solar power installation will be about 20 megawatts.